Hi students, welcome to Year 9 Science and Unit 1 Atoms and Stuff, and we're looking now at video 8 and the last in our little series of looks at some of the key scientists who progressed our understanding of the model of the atom. And this time we're going to be looking at Niels Bohr. As we've gone through these last couple of videos, we've been trying to describe the structure of the atom in terms of the location and identity of protons, neutrons and electrons. And of course the key in this particular one, the discoveries that were put together by Niels Bohr, was the actual location of the electrons. So the problem for Niels Bohr was this death spiral of electron. Why didn't the electron wherever it was orbiting the nucleus eventually lose sufficient energy that it just went on this endless spiral until it hit the nucleus and was annihilated? Bohr was a Danish scientist early and did a lot of his work early in the last century, in the 20th century. He also studied with Rutherford, so he was familiar with the work of Ernest Rutherford and also that solar system model that Rutherford had put together. But Bohr was also aware of the work of Max Planck in the quantum area. Now, quantum theory is quite complex, and it's something that we really want to save for the senior years and probably into university. It has, however, had a contribution, and it does help us to look at atoms in such a way that makes them really useful tools to explain what happens in chemical reactions. And so therefore, we need to have just a quick look at what it was that Bohr put together with Rutherford's model and Planck's work in quantum theory to construct a model that is a really, really good approximation for what's happening with the atom, but more importantly, that is a great predictor of how atoms behave in chemical reactions. So the key for Bohr was this whole idea of stable energy levels. So to overcome the problem of the death spiral for an electron, what he said was there are certain regions of space around the nucleus where the electrons can exist, and they can exist in those orbits forever. If you want to move them out of that orbit, you need to add energy to move them further away from the nucleus because of the force of attraction between the positive nucleus and a negative electron. These are going to be attracted to one another, so the electrons are going to want to move towards the nucleus. And just as we on Earth orbit the sun and the moon orbits the Earth, things will go in a circular or elliptical orbit indefinitely if there is a force of attraction between them, and provided that force doesn't become too large or too small. If it becomes too large, then the orbiting object will start to accelerate towards the center. If it's too small, then it'll lose its influence and it'll start to pull away from those orbits. But Bohr said, based on quantum theory, that there are stable levels. And if you put a certain amount of energy in, you can actually get these electrons to move from one orbit to another. And in this case, as you can see here, from level number 2 to level number 3, we have to put a certain amount of energy in. When that excited electron releases that energy, it returns back to its previous, what we call its ground state. So ground is where it starts, and to take in energy it moves to an excited state. So energy in, and when it's going back down again, that energy goes out. And in fact, when we look at things like flame tests, when you look at fireworks and you see the colors that are produced, what you're seeing is the movement of electrons from their excited state where they've taken in energy and gone to a higher energy level, and then as they return, they release that energy as a specific wavelength, which sometimes corresponds to parts of the electromagnetic spectrum that we can see, called visible light, and so they look as a particular color or combination of colors to our eyes. So what was Bohr's significant contributions then? Well, he said the electrons orbit the nucleus at different and specified energy levels. Only the electrons with specific amounts of energy could exist at each of those levels, and there are different numbers at different levels. And the electrons could move from one level to another by gaining or losing packets of energy. We've called these photons or quanta, and they take a certain amount in to move from one level to another, and they release that again when they move back from the higher excited state back to the lower ground state. So that gave us a model which has been pretty much the most useful model that we have for explaining a lot of the behavior that we see, and for the chemical reactions that you'll see, the way that atoms can be converted into ions, positively or negatively charged atoms. The Bohr model is a very successful and a very useful one in terms of predicting what's going to happen. It's not the full story. It doesn't explain things at a very deeper level of quantum mechanics, but fortunately that's not something that we need to worry too much about in the Year 9 course, and something that you may look at in chemistry courses in Years 11 and 12 and beyond. So this just gives us a little bit of an understanding of our current model of the atom, and the one that really helps us to focus in on explaining the behavior of matter. The most important contribution, of course, is the fact that the electrons are in specific energy shells. That's the thing that Bohr improved on from those models of Dalton through Thomson and Rutherford, and the one that's the really good explanatory one for what we use today. Thanks for watching.